Hi, this is Home Group 3's presentation on the filter design for audio signal. First, we're going to directly go into the audio read where Y and Fs is the obtained data, and also the Fs will be our sampling frequency. Next, we can immediately use the sampling frequency and the length of the data obtained to obtain the time frame. Next, we can immediately plot the time frame to the data, which we can get two formats, which is the plot or stem. This is the plot one, and this is the stem one. Next, we can immediately go into the frequency domain where we can immediately get the frequency domains, the sampling frequency, so we can immediately get the frequency spectrum, and then we use the FFT, the fast Fourier transform, where we use the data and also the sampling frequency to obtain the frequency domain, while we use the absolute to obtain all in positive spectrum domain, and then we can really plot it. Which will be obtained is this. If you look at this spectrum graph, you can immediately see that there's a oddity right here on 800 hertz, where this is an oddity, and also there's too much additional noise beyond 2200.
That is Z domain analysis, which we can plot it using Z plane VA, which D is numerator and A is denominator. So to get the Z domain, we can use Z transformation from time domain to Z domain using short Z transform function, which is CZTF, which F is the time domain signal. Then we can transfer from Z domain to frequency domain by using FREQZ, which we can determine the sample using this function. Then from Z domain, we can transfer back to time domain plot using IMPZ, which we also can determine the number of samples using hash, and T is the sample times, and N is the number of samples. So this is the method code for Z transform. This is the plotting in Z plane, and this is the plotting for the Z domain graph after the signal has been Z transformed. And this is the graph for the impulse response. Then last is for Z domain to frequency domain plot. We use the frequency Z Y1 to convert from the Z domain plot into frequency domain plot.
In this code, I'll be discussing about the filter design. So for D1 and D2, we used it for the FIR frequency. So we used order of 200 and a cutoff frequency of 750 and 950 for D1, and for D2 we used 200 cutoff frequency of 200 and 2200. For D3 and D4 we used it for the IR frequency. So we used the 18th order and half power frequency of 750 and 950 frequency for D3. For D4 we use 200 frequency and 2200 frequency. And this part is to start the bandpass for IR frequency. So we use the 18th order of 750 and 950, and for B2 we use the 200 and 2200. And for the results, let's see the graphs before and after. This is before frequency domain, and this is after it filtered frequency domain. As we can see, there's a huge difference in the noise here and here.
I'm going to present about the post and zero analysis of the filter. So after the filter analysis, we can use the Z-plane function to check the stability of the filter. So for the function, the input is B, which is the numerator, and A, which is the denominator of the filter. So the output will be a zero pole plot. So this is a table to summarize the type of filter, the code, and the zero pole plot of the FIR filter. So for the band stop filter and band pass filter, we can see that there is only one pulse and it located at the origin. So this table is to summarize the type of filter, the code, and the zero pole plot of the IR filter. So for the band stop filter, we can see that all the poles are inside the unit circle, indicate the filter is stable. So same with the band pass filter, we can see that all the poles are inside the unit circle, also indicate that the filter is stable. Thank you.
The three expression and function mentions serve the purpose of implementing digital filter. The expression y equal convolution hash x represents the convolution of two signals, which is hash and x, where the hash is the impulse response of the filter, the x is the input signal. Y represents the filter output signal. The purpose of the expression is to apply the filter defined by hash to the input signal x. Convolution is used as a method of filtering in the Z domain. So the second one is the filter function. The expression y equal filter Ax is used to apply the filter to an input signal x. The filter is defined by its numerator coefficient B and the denominator coefficient A, and the filter output signal is written as y. This expression can be used for both FIR and IR filters, and the Z domain is used for the filtering. So the third one is the expression of HD and ZD. Is used to compute the impulse response of the digital filter D. The impulse response H represents the filter's response to a delta function input, and the T is the time at which each sample of H occurs. The purpose of computing the impulse response is to analyze the behavior of the filter or to convert an IR filter to an equivalent FIR filters. So in summary, this expression and function serve the purpose of implementing the digital filters by defining the filter transfer function, apply the filter to an input signal, and compute the impulse response of the filter. The Z domain is used for filtering, and the impulse response is used for analysis and conversion of filter. So that's all.
So this is the result of our filter. So this is the original audio.
0125.
So we can hear that there is a noise. Then this is the filter audio using the FIR filter.
0125.
So this is the filter audio using the IR filter.
0125.
So from the audio, we can hear that by using either the FIR filter design or the IR filter design, we can remove the noise from the audio. Thank you.